Okay, so now we're going to look at actual data. Okay, now remember, we'll get to these numbers in a second, but your theoretical bell curve is just a basis of comparison, and it correlates with the standard normal table that you'll find in the back of your book, which is at Appendix Z, or Appendix B. So, some of you might remember back in 2008, they had the Olympic Games in Beijing, China, and there was this runner named Usain Bolt. He ran the 100 meters and the 200 meters, and he was kind of a big star. He won both events, and what we have here are the 2008 Olympic Game 100 meter finals for men. So here's Usain Bolt in red and all the other 7 runners, so 8 runners total, with their times. So this is in seconds. So Usain Bolt ran the 100 meters in 9.69 seconds. And you can see his time is considerably faster than all his 7 competitors. Okay, so what we want to see is when we take this actual data, how it compares to our theoretical construct of the bell curve and place it in the standard normal table. And we do that by getting a z-score specifically for Usain Bolt. Now we could get a z-score for any one of these competitors' times, but we're going to look at Usain Bolt and see if he is an outlier relative to these other competitors, to his peers, and if he's an outlier to a degree that reaches statistical significance. So, in order to do this, first off, we have to calculate the mean and then the variance and the standard deviation. And I'm not going to go through all that. You learned how to do that last week. Now remember, we have an n size or sample size of 8 because we have 8 competitors. If you add up all these 8 competitors' times and divide it by 8, you get the mean, which ends up being 9.92 seconds. Now remember, we need the mean in order to calculate your variance and then standard deviation. If you go through that lengthy process, remember you subtract each score, you subtract the mean from each score, square it, add them up, get the summation of all those, and divide by your n-1. That gives you your variance, then you get the square root of that, that gives you your standard deviation. Go through that whole long process, you get a standard deviation of 0.105. Okay? Now let's look over here. We could get a z-score for any one of these competitors, but we want to get the z-score for Usain Bolt. So the z-score formula we have up here is you take whatever score you're looking at, you subtract the mean, and then you divide by your standard deviation. And that will give you a z-score for that particular value. Okay? So if we do it for Usain Bolt, our z-score equals his time of 9.69 seconds minus the mean of 9.92 divided by your standard deviation of 0.105. So one more step, negative 0.23 divided by 0.01, and you get a z-score for Usain Bolt of negative 2.19. Okay, so now you have to go to Appendix B, and you're going to have to do this on your own and look in your standard normal table. But remember before when we looked at the bell curve, we had z-scores of 1 that was about here, 2 that was about here, or negative 1 and negative 2, and positive 1 and positive 2. So what we know is that Usain Bolt's z-score is negative 2.19. It's way over on this left side of the bell curve, or the left tail. It makes him, that shows that he's very unique relative in comparison to his 7 other peers in this final. We can call him unique, unusual, or significant. The area beyond Z, so you have a z-score here of 2.19, and the area beyond Z is 0.0413, or what we can say is on this little bit of the tail is only 1.43%, right? We can take this fraction, move the decimal over 2 places, and you get 1.43% of the, he represents that little bit relative to the entire rest of the bell curve. Okay? Now if you go into your Appendix B, you can see that there are different labels. So 2.19, it'll say the area between mean and Z is basically 50% minus this 1.43. Or it'll be about 48.57%. Okay, but the area beyond Z is really the column you want to look at in terms of determining statistical significance. And it's 0.143 or 1.43%. Again, the greater your distance between the mean and your z-score, the smaller this area beyond Z is going to be, and that makes it more significant. Now last thing, we want to say, how can we create these thresholds or standards for statistical significance? If you have a z-score of 1.65 or more, and that can be either negative or positive, but if you have a 1.65 z-score or higher, then you're going to have an area beyond z of 0.05 or less. Okay? That would mean that the person's score is significant at the level of 0.05. If you have a z-score of 2.33 or more, that could be negative 2.33 or greater distance from the mean, or positive, then you're going to have a level of statistical significance at 0.01. Okay? Here's how we determine this. Usain Bolt z-score has an area beyond z of 0.143. That's less than 0.05. So his score is statistically significant at the threshold of 0.05. Or what we can say is there's a 95% probability that his difference in score between the rest of his competitors did not happen by chance. We can say instead that there's a 95% probability there's something significantly different between him and all his other competitors. Okay? His score of 2.19 does not reach the threshold of 0.01 because 0.0143 is actually bigger than 0.01. So we cannot say that it reaches that threshold of statistical significance. Okay? But we do reach the threshold of 0.05. Okay? So there's a 5% probability that his difference only happened by chance, or a 95% probability that it did not happen by chance, meaning there's something significantly different about him and all of his peers. That could mean something really bad, like he took steroids, and I'm not saying he did because he was never caught for that. Or it could just mean something totally different, like he's just that much more talented than his peers. Somebody might explain it by saying that he's unusually tall for a 100-meter runner. He's like about 6'5" or 6'6", whereas most 100-meter runners are relatively short. They're about 5'9" to 6 feet. That's because most people who are shorter their legs can move faster. But him being tall, he has longer legs, and if his legs move just as fast as his competitors, then he's going to run that much more faster. Maybe that's what makes him significantly different from his peers. And we can say with 95% confidence that there's a 95% probability there's something significantly different between him and his peers. And we did that by determining the z-score.